Okay, so in the last video on electric current, we had just defined what resistance is. Anything that you wire into a circuit has some resistance. The resistance is given by the ratio, by dividing the potential difference before and after the object, the part that you put into the circuit, divided by how much current is flowing through that object. The bigger the potential difference, the more the resistance. The more energy is used up at that spot, at that object, at that piece of the circuit, the bigger the resistance is. So what we see from this is that each part of a circuit is associated with a drop in potential difference or voltage in the circuit. Any circuit component that has a resistance is associated with a loss of energy. Because remember, if the voltage is decreasing, that means that each charge that passes through that part of the circuit is giving up some of its energy. Okay, remember, voltage is not the same thing as energy, but it's very, very similar. We can see that if we go back to the simulation and we wire up a little circuit here. So we're going to do battery. Okay, wires. We're just going to connect this to a resistor. Nope, there we go. Okay. And there we go. Okay, so we have charges flowing. I'm going to do conventional current just because that's what we're most used to. I'm going to do values. Okay, so what we see now is that this battery has a voltage, a potential difference of 9 volts. The resistor has a resistance of 10 ohms. Now we can double check that if we look at the potential difference across the resistor. Okay, see how that potential difference, that voltage, notice I'm connecting the voltage across the resistor. If I don't include the resistor, then I don't get any voltage. But if I'm including the resistor, so I have probe, resistor, another probe, I get a potential difference of 9 volts. And I have an ammeter that can measure the current anywhere. So I'm measuring the current, it's 0.9 amps. If the voltage is 9 volts and the current is 0.9 amps, voltage divided by current should give me the resistance. 9 divided by 0.9 is in fact 10. Matter of fact, this will be the same if I increase the value of this resistor, which I can do. There we go. So if I increase the resistance, let's say I make it, I don't know, 20 ohms. Oh, I almost had it. There we go. If it's 20 ohms, then the voltage is still across it is still 9 volts. The current is still 0.45, or is now 0.45. If I divide those two, you get 20. So the resistance is the product, is the quotient of the voltage drop across that piece divided by the current. Okay, so anytime we have something in a current, it's associated with a loss of, for a potential drop, which is ultimately associated with a loss of energy. Remember, resistors give up energy by changing that electric potential energy into heat. Okay. So you'll see this word a lot. Voltage drop leads to a loss of electric potential energy. It gets turned into something else. Now, another very, very important fact, probably the most important fact with a circuit, is that the total voltage drop in a circuit is equal in magnitude to the voltage gain inside a battery. Batteries are associated with voltage gains. Okay, they increase the energy that charges have. Other things in a circuit, the power consumers, the energy consumers, they decrease the energy. They take that energy away from those charges. This is just an example of conservation of energy. So whatever the voltage gain for a circuit is from its battery, the total voltage drop in the circuit must be equal in magnitude to that. Again, so actually here, I'll draw this out for you and then I'll demonstrate it. So let's say that we have something like this. We have a 6-volt battery connected to a resistor. A 6-volt battery means that the gain the voltage gain between terminals, between the ends of the battery, is 6 volts. Therefore, there must be a 6-volt drop somewhere throughout the circuit. To allow this to happen. Okay, and that's why the short circuit is bad. The short circuit, there's no place for a voltage drop in the wires, so what ends up happening is the current gets too big, and therefore everything catches on fire. And that drop, in this case, happens at the resistor. So, we're going to go back here. I'm going to make this bigger so it's not quite as, it's kind of shrunken down in there. Okay, make that nice and big. I'm just going to cut this, move this up here, and there we go. Okay. So we have our nice spread out circuit. We see that we have a voltage gain. We can hover over the current anywhere. And notice that the voltage for the battery, the voltage drop for the battery is equal to the voltage gain of the battery. Or excuse me, the voltage drop for the resistor is equal to the voltage gain for the battery. And that's going to be true no matter if I increase the voltage. I increase the voltage to 54. The voltage drop at the battery is now 54 also. And that'll work. I can increase this up to 120 volts. That'll be true no matter what I have this on. Oh, this is in hundredths now. That's interesting. It used to just be in tenths. Or no, in every 500ths it would go. Oh, this was a 9-volt battery. There we go. Okay, so some other things that we can see here. If I change the resistance, we kind of already saw this. If I change the resistance, if I play with this, it's going to change the current. Does not change the voltage drop at that battery because the voltage gain, or the voltage drop at that resistor, because the voltage gain of the battery also didn't change. So let's bring this back down to 10. Okay. Let's see what else. Matter of fact, that'll even be true if I break the circuit temporarily and I add in another resistor. Let's put another resistor in there. And just for fun, let's make this one a different one. So let's make this, I don't know, like 20 ohms or something. Oh, that's not going to work. There we go. Okay. So notice that now that I have another resistor in there, the current has changed. The voltage from the battery, the voltage gain has stayed 9. And now the voltage drop at this resistor is 3. Well, let's go and let's check out the voltage drop for just that other resistor. And look at that, it's 6. So I have a voltage drop of 3 around the 10 ohm resistor, voltage drop of 6 around the 20 ohm resistor. The total voltage drop I can get by putting the probes around both of these, kind of like we're combining the resistors, and that is now 9 volts, equal to, once again, the voltage for the battery. Let me show you how it, so this is how a voltmeter works. Notice that we're almost making like an alternate path for the current, and that's how we're measuring. That's how they get measured. Let's get rid of this. Let's show you how an ammeter actually works. This is a real ammeter. Ammeters get wired right into the circuit, so you have to actually physically connect them like this. Oh, okay, there we go. Notice it says the exact same thing. It's still 0.3. Okay, so we've got a lot of things that we can demonstrate here, okay? And this is just a very basic circuit, but we see that it's all kind of linked together, okay? If we change the voltage of the battery, again, the total voltage will change. Let's make it 56, but we still have the sum of the voltage drop, so 37.33 plus 18.67. You can do that in your head or on a calculator. You'll see that the total voltage drop is still equal to the voltage gain for the battery. Okay. Notice that the current has also gone up because we basically changed the voltage. The total resistance remained the same, so the current also had to go up. There's tons and tons and tons of things that we can demonstrate with the use of this little circuit animation, this application. So we will be coming back to this many times, okay? But right now, what I really want you to understand is that everything that you put into a circuit can have a voltage drop. Matter of fact, the last thing I'm going to do, I'm going to take this out for just a second, and we're going to put in a light bulb. Okay, and you see that we still have a voltage drop from the light bulb itself. And you can see that not only does the light bulb give off heat, but it also gives off light. And matter of fact, if we change the voltage of the battery, we can increase or decrease the amount of light being given off by the light bulb. That's kind of fun. We can also change the internal resistance of the light bulb to increase or decrease the amount of resistance being given out. So that's kind of neat. Okay? So, again, what I want you to really focus on here, the key takeaway, is that the voltage gain for the battery is equal to the sum of all the voltage drops in the circuit itself. Okay? And that anything that you put into a circuit has a voltage drop associated with it. The last thing that I want to talk about with circuits before we start kind of playing around with them is wire resistivity. Now, if you noticed, and I'll go back to this in just a second, if you noticed, none of the things that we did so far changed the even when we had the probes around on just the wires, it said that the voltage drop for the wires was 0. And that was actually because we didn't have this set to have any wire resistivity. Wires actually do have resistivities. They're very low, but they are measurable. You can calculate the resistance of a wire using the following formula. R equals rho, that's a funny looking P, you can kind of draw like a P with a little tail curling to the right, times L over A. Rho is known as the resistivity. I'll talk about what that is in a little bit. L is the length of the conductor, basically the length of the wire. A is the cross-sectional area of the wire, basically how thick it is. So we have this formula. R equals rho L over A. I'm going to define what all these things are. R is obviously the resistance. Rho is known as the resistivity. Resistivity is a property of different metals. It's a physical property that a different type of that every metal that we could use as a wire has a different resistivity. It's just like saying like what's the density of something. Okay, resistivity is a property of the different metals that we use. And if you look on the reference tables, there's this nice handy table that actually tells us what the resistivities are. So I'm just going to put that we need to look in the reference tables for this. Down here in the bottom right on the electricity page is resistivities at 20 degrees Celsius. And it's important that it's at 20 degrees Celsius, okay? Here's all the different materials: aluminum, copper, gold, nichrome, silver, tungsten. Here are their resistivities, given in ohms times meters. Notice that they're all very small, like times 10 to the negative 8th. However, one of them is much bigger. Notice that nichrome, even all these are below about 5.6. This is 150. So nichrome has the largest resistivity, okay? You'll notice that the second lowest one is copper. We have lots of copper wires around. It's because copper is a very low resistivity. If you look at our equation, the lower the resistivity, the lower the resistance of a wire. We want wire resistance to be very low because that means that energy loss isn't going to occur at the wires. We don't want energy loss to occur at the wires. We want it to occur at the resistor or at the lamp where we're actually trying to dissipate the energy. So the reason that we use copper wires is because their resistivity is very low. They allow electrons to move very easily. Okay, these are all conductors, but not all conductors are created the same. Some allow electrons to move more easily than others. Copper is allows electrons to move very easily. Matter of fact, the only one that's smaller for resistivity on here is silver. So you might say, why don't we have silver wires? But think about it. Copper is much more abundant than silver. It's much cheaper than silver because of that. So we use copper wires, okay? The difference is like less than 10% anyways for copper and silver. So anyways, resistivity, the lower the resistivity, the less resistance that wire has, and the less the resistance, that means that there's going to be less of a potential difference given a certain current. L is the length of the wire. Very self-explanatory, and from this equation you can predict that the longer the wire, the more resistance there will be and the more energy loss there will be. going to go back up to the simulation one more time, and we're going to turn up the wire resistivity. We're going to turn it up from tiny to lots. Now watch what happens. The battery voltage is not going to change. The resistances are not going to change, but watch what happens to the current. That current just went down because I just increased the resistance, okay? I just made it harder for charges to get through the circuit. That will decrease the current. If I had wire resistivity down back to tiny for a second, and I put these probes up here, notice that there's no voltage change. Okay, the voltage change, it says 0. As I increase, if I go up to lots, hey, now there is a voltage difference between these 2 points because the wire has some measurable resistivity. And watch what happens if I decrease or if I increase that length. The voltage drop goes up. So the longer the wire that I'm looking at, the greater the resistance, which means the greater the voltage drop. Smaller wire, smaller resistance, smaller voltage drop. Just like we see in our notes. Okay? Big wire, big resistance. If there's a big resistance with a certain current flowing through, bigger voltage drop. And vice versa. Smaller L, smaller resistance. If it's a small resistance with a certain current flowing through, smaller voltage drop. A is the cross-sectional area of a wire. Cross-sectional area basically means if you were to take this wire, and it actually kind of says it right here, slice it so that you expose one of the faces. This right here is the cross-sectional area, this area right here of the circular face. Okay? The bigger the cross-sectional area, the less the resistance. And we'll talk about why that is in just a second. And then finally, there's something that's not on here. I need you to know this. The resistance will increase. It goes up if the temperature goes up. Okay? Things that get hotter typically have greater resistance. To close this video, we're going to talk about why this equation makes sense. We'll start from we'll start from the more resistant material. Okay? The first part that we talked about. So if you have a more resistant material, so if the resistivity is higher, I should say more resistive, I suppose, because it's resistivity, not resistance. If rho, the resistivity, is higher, that means that it is harder for charges to move, and therefore they have to use more energy to move. They have to give off more energy in order to move and keep the current flowing, which leads to a higher R, just like it shows in the equation. For a longer wire, well, the longer the wire gets, the more energy is needed to get the charges to the end, which also results in a higher R. For a bigger cross-sectional area, that essentially means a thicker wire. A thicker wire means that there is more space for more charges. Okay, the charges can spread out a little bit more, so they can accommodate they're not going to hit into each other as much. They can accommodate a bigger current that reduces the resistance of the wire. And then finally, a hotter wire. Remember what happens to hot objects from chemistry. The hotter an object is, the greater its kinetic energy, typically, which means it has more speed. And you might think more speed means they get through quicker, but what ultimately ends up happening is more speed means more collisions, more energy lost due to unwanted collisions. More unwanted collisions and unwanted energy loss, which means higher resistance. Okay? More collisions means those charges are giving up energy where they're not supposed to, which, since they're giving up more energy, the potential difference is going to be greater. Therefore, the resistance of the wire is going to be greater. So that is electric current in a nutshell. I'm trying to think what else there is. I think that's pretty much it. Where we're going to go from here is we're going to look at different types of circuits. So we're going to spend some time looking at series circuits and parallel circuits this year in class. Both of those are pretty straightforward. There are some rules for each type of circuit. You need to be able to identify what type of circuit you're looking at, but there's some rules that you need to learn, which we'll talk about in the next few videos, and then you'll be on your way to making very simple electric circuits and being able to understand and analyze them. I'll talk to you later.